Okay, good morning everyone. My name is Jan and I'm working at the Zurich University of Applied Sciences in the group of Mark Zillibach, where we focus on text analysis. In our work we also use deep learning, and today I will sort of give you an overview of how well deep learning works for text, how it performs, how it is used, and where the limitations and challenges still lie. So, as you know, deep learning is some sort of hype theme for the past few years. And rightly so, because it really generated a lot of very good results, especially in computer vision. What you see here are the results for the ImageNet challenge a few years ago, where deep learning was applied the first time very successfully on image classification tasks. And what I want you to note here is the first time that they used it, the error rate dropped by 10%, which in such classification tasks is a huge number. Usually you get an improvement of 1% or 2%. So today I will sort of talk about how well does this translate to text. Do we get the same improvement as we did for computer vision? For this I will present three sort of showcases where we apply deep learning on text classification tasks and sort of make my points using those examples. But before we do that, we need to talk about the input to our classifier. For vision, it's pretty clear. You take your raw image and you feed it into your neural network. So in text, we cannot do this. The reason is because in text, we have strings of characters that don't have any inherent meaning to our computer. So what we need to do is sort of encode or find a representation of our vocabulary so that some sort of semantic is encoded into this representation. And the standard approach for this is called word embeddings. Previously it was known as distributional semantics. And essentially the idea is to encode the words that you have as vectors in an n-dimensional room, so that the vectors have some sort of semantic meaning based on their positioning. So what you have, for example, is that synonymous words are very close to each other in this n-dimensional room. Also, also there are some other properties that are encoded in this n-dimensional room. Sort of, we have different, we have the concept of male and female, where the distance between king and queen, or the vector between king and queen, is the same as the one between man and woman, or at least parallel, more or less. And we have other concepts encoded as well. So the way that these embeddings are generated, there are different methods you can use. There's word2vec, GloVe, fastText, and so on. But what they all have in common is sort of the idea that you use sort of the context in which words appear. Sort of you exploit this information to create these embeddings. So for example, in GloVe, you create a huge table where you write in for each pair of words if they appear in the same context. And then you do some sort of matrix factorization to create the word embeddings. Okay, there are other techniques, but I will not really go into them. So, oops. And again. All right, so the input to our neural network is, we have our sentence we want to classify. So what we do is we do some tokenization, and then for each word, we get the corresponding word vector, and then we just concatenate the word vectors of all the words to sort of create this sentence matrix. And this is our input. So as you see, it's sort of in schematics pretty similar to what you have as a picture. You just have like this n times k matrix. So now we look at our networks. I will not go into the details of how these networks work, but what I want you to know is that what all the networks do, regardless if they are convolutional, LSTMs, or whatever, what they do is they take the sentence matrix, they do a lot of computations that they learn during training, and then they create some sort of sentence embedding. So what they do is they take this matrix, do computation, and then embed or create a representation for our sentence, which you can use for classification. Otherwise, I will just treat these neural networks as a black box for now. Okay, now we can look at the tasks. The first task is sentiment analysis in a multilingual setting. So the task is to, given a text, we want to classify its sentiment as either positive, negative, or neutral. And we did this on Twitter data. Okay. The problem with neural networks, which is very known, is that neural networks need a lot of data, which we usually don't have because it's costly to generate. So what we did here to sort of mitigate this problem is we use this three-phase learning approach, where we first use a corpus of 300 million tweets to generate our word embeddings. So we have our word representation for our vocabulary. Then in the second phase, which we call the distant phases, we take a huge corpus of tweets which have emojis or smileys in them, and then we just infer the sentiment just by looking at the emojis. So if we have a happy smiley in the text, we say it's a happy tweet or a positive tweet, and the same for negative. So we take this corpus of 40 to 60 million tweets, and we train our neural network for one epoch on this data. And this sort of pre-trains our neural network, and also it adapts the word embeddings to sort of encode also some knowledge about sentiment. All right, after we did that, we have this pre-trained network, so we finish the training by taking the annotated data, which is usually about 10,000 tweets or 20,000, and then we train it for a couple of epochs more. So, just to take a look at the data. We have used this tried this approach for different languages. So for English and French, we have 60 million tweets respectively, and for German and Italian, we have 40 million. And they are a bit unbalanced, but that's okay. For the supervised phase, it's a bit different. We have a lot of tweets for English, almost 20,000 tweets, 10,000 for French and German respectively, and only around 7,000 for Italian. So as you see, it's a bit skewed toward English, but that's a bit normal, I guess. And the English data we got from SemiWal 2016, which is a shared task for semantic evaluation tasks. Sentiment is one of them. So these are the results. Doing this three-phase training, we get for each language around 65% in F1 score. However, if you do not do this distant phase, if you omit this huge corpus of weekly supervised data, you get on average 3 points less. And also you see that not doing the distant phase, you get results that are similar to an SVM, which was sort of trained on a lot of hand-crafted features. And the random forest we have just as a baseline trained on n-grams. All right, so then also this is sort of the state of the art. We won 2 competitions, the SemiWal last year, and the Evalita also last year, which is sort of the Italian equivalent. Don't get confused, we just had a late submission, that's why we are down here, but the score is better than in the first place. So. Okay. As a short summary, so deep learning is very easily adaptable for multiple languages. So you don't have to recreate your features, which are very language dependent. So you have different grammar rules for German, French, and so on. But in deep learning, you can just take your data and train your model with that. However, we have also seen that it's very data intensive. So you need a lot of data to get good results. Okay, let's look at the second task, which is sort of author profiling. And in this case, we want to know for an author if it's a male or female and which dialect they speak. So variety refers to, for example, is it American English, British English, Australian English, Jamaican English, and so on. And again, we work on Twitter data, but this time the setting is a bit different. We get for each author a set of 100 tweets, and based on these 100 tweets, we need to classify the author, like for these two tasks. The data has been provided by the PAN 2017 shared task, which is sort of for author profiling and so on. And the data is very, very high quality. So for each, we have again 4 languages, and for each language we have a couple of thousand author profiles. So for English we have 3,600 profiles, and each profile has 100 tweets. And also the data is very balanced, so we have a 50-50% split for gender. And for the variety, we have 600 authors for each variety. Like for example, for Portuguese, we have Brazilian and Portugal Portuguese, and we have 1,200 authors. So very balanced data set, very nice data for change. Okay, then the results were done as a bachelor thesis, which we supervised last semester. And these are the results that our guys got. So they used a GRU, which is some sort of, as you can think, a lightweight LSTM. And they got very good results. For gender, they had like around 70 to 80% accuracy, and for the variety, they even got above 90% in these two cases, which is surprisingly good. Also, they tried different architectures like CNNs, LSTMs, and GRUs, and what you see is that CNNs in this case sort of didn't perform that well. Okay, in summary for this task, if you have good data, you tend to get better results, which is sort of clear. But the other point is that in deep learning, if you think about it, we go from feature engineering to architecture engineering. So instead of spending a lot of time in generating our features, we spend a lot of time in finding and tuning the perfect architecture for our task. Okay, just quickly the last task, because I have a bit of time constraints here, is community question answering. In this case, we have, you know, these forums where you can ask your question and then a lot of people reply to your question. And the main problem here is that the replies aren't really always relevant to your question. So what we want to do is we want to re-rank the replies to a question so that the relevant ones are on top. The data is again from Semival 2017, and we get for each question we get 10 potential answers. And what we do is we model the task in classifying question and answer pairs. We get a question and a potential answer, and we sort of classify if this pair of question-answer is relevant or not. And then we use that, the score for re-ranking our answers. So we got 22,000 pairs for training, 3,000 for validation, and 12,000 for testing. The approach is a Siamese convolutional neural network, which is sort of, you can imagine that as 2 parallel neural networks that take the question, take the answer matrix, which we discussed at the beginning, and create question embedding and the question answer. And then we just concatenate these 2 vectors and use this joint representation to classify this pair of question and answer. As for results, we participated at the Semival task. We got okay performance. You see that you have here a group of all these, they all have all neural networks as their approach, and they all got like 86% in mean average precision. However, the KELP group, they used a feature engineering approach. They really sat down and created a lot of features, and they really got the best results, and they are 2 points above all the deep learning approaches. So as a summary, we know that we saw that deep learning supports a large variety of architectures. We just saw the Siamese architecture. And however, on the other hand, we have still not the problem. We still see that feature-based approaches also work very well. And in this case, they even outperformed all these deep learning approaches. So, as a conclusion, we saw these 3 tasks. And the main learnings that we got is deep learning is very data intensive. So if you want to apply deep learning in your company or whatever, you need a lot of data, and then you need a lot of quality data, and which is always very hard to get. And for text, it's not always the case that it is better than the feature-based approaches. So maybe you want to evaluate which approach you want to use, if you really want to go the deep learning route, or if you want to stick to some feature-based or even rule-based approach. And the other thing is, you don't get really a time reduction by using deep learning approaches. You really need to put a lot of time in this architecture engineering. And also, it takes a lot of time to train these neural networks. So in conclusion, neural networks, if given in the right context, give you very good results. But if you really want to apply it, you need to think about if you really can meet all the requirements that are needed for training a deep learning architecture. So that was it. Just as a quick side note, we open sourced the code for the sentiment analysis. So the whole sentiment analysis code is up here, and you can download it and play with it and so on. Okay, thank you very much.
We have time for one question. I think we are a bit short of time. Yeah?
So maybe you don't need to go back to the slides, but my question would be for the architecture. You said you have tweets, and each word has an embedding space, so that's size k, I think you used it.
Yeah.
But then you have several words, so your encoded space is a matrix of n words of length k.
Yeah.
And my question is, what do you do, because tweets have different length of the number of words?
Yeah.
So what is your input there?
This is a sort of no problem. If you have, you just define a maximum length of tweets. You say a tweet cannot have more than 60 words. And then if a tweet is shorter than that, you just pad it with 0 or some dummy embedding. So there's just a padding of some dummy embedding that you use for saying that this is nothing. Yeah.
And then the neural net figure out the change.
Yes, it figures that out.
Okay, unfortunately we don't have time now for any more questions. Please ask him in the coffee break. Then thanks the speaker, and we go over to the next.